to use in some area, some application, and for some it has a different constraint also. And also we will be discussing about the motor controller part, and some of the, like, we have done some innovation on that area, so we will be discussing on that. So moving forward, particularly we have been seeing that there is a increasing demand for the electric vehicle and solar. So it is expected that by the 2030 we'll have around 500 million EV to be on the road. And what is the main reason? If you look into the growing demands, is particularly the technology advancement in the lithium battery technology, the reliability of high efficiency inverter, and the evolution of different types of electric motors, and particularly the cooling technology. When we talk about power electronics, our thermal design is very, very important. So recently there is a lot of advancement and innovation has been done in that area. Second thing is, when we talk about EV, the user range anxiety has been a problem since a long, and different industry and government initiative has been taken on this field, particularly to reduce the user anxiety by adapting to technology, reliability of products, battery swappable, and fast charger, as well as both DC as well as AC fast charging has been done in this area. The most important challenges what we face is like how to design a very reliable product and keeping a very cost optimized product, so it can be suitable for the consumer as well as for the industry. So that is where the real challenge comes. And second field is definitely the solar field. Solar, there is a energy is available to everyone, is accessible to everyone, and it is a clean energy. And definitely we will try to develop a power converter where we have a very high efficiency, is a reliable product, and as well as we will be able to meet different standards, particularly the IEEE 1547, as well as the UL standard for, and California standards. These are very important when we talk about the safety and of the consumer. Yes, moving forward, we'll be starting with the gallium nitride. As most of you might have known about this gallium nitride, it has been talk of the industry, and because it has a very high potential and future is moving towards gallium nitrates, but it has some limitation, and which will discuss today, and what are the different type of GaN structure are there in the industry, and which are being used particularly for research as well as in the industry. So GaN particularly has it facilitates us very high switching speed. It has a very higher background strength, faster switching speed. It has a good thermal conductivity, lower on resistance. And when we discuss about the critical field, gallium nitride is significantly better compared to silicon carbide and silicon MOSFET. So right now there are like three main type of GaN which is available. One is like GaN on silicon, and second is GaN on silicon carbide. Third one is GaN on GaN. So GaN on GaN is a recent technology where if you look into the device area remains three for all the technology. But if you look into the carrier wafer, how it has been done, how the structure is being incorporated into that, so that can differ. So it can be a silicon or silicon carbide, or it can be a GaN. So particularly GaN on GaN is a vertical device, whereas GaN on silicon or GaN on silicon carbide is a lateral device. Second thing is GaN, we can operate in three modes. Like one is the depletion mode, where usually it's remain in normally on condition. Then second is enhancement mode, where it will be usually remain in off condition. And cascade mode is basically a integrated device, like it will be integrated with the silicon as well as with the GaN. So we'll discuss into that in detail. So let me introduce you to the this vertical GaN technology. So vertical GaN technology is a patented technology, and it has been developed by a company called NextGen, and we are collaboratively working with that. And particularly vertical GaN allow us to work in a very high frequency and in a very high voltage. The breakdown voltage is very high for this one. So why how we are getting this very high breakdown voltage is basically the how it has been the fabricated is very different way. And second is it is a homogeneous structure compared to GaN on silicon or GaN on silicon carbide. It is a heteroaxial structure. So you can see the, if you look into the two picture below, So particularly the GaN on silicon is a lateral device where the distance, particularly how the breakdown voltage is basically the voltage when it is in off condition, and like what is the distance between your gate to drain. So that's define your the breakdown strength of that. And if you look into the vertical GaN, we since it's a 3D dimensional structure, and it allow you the more distance between your drain to source. So that's why sorry, gate to drain. So we usually will have a more distance, and that's why the your breakdown voltage also increases a lot. And but it has a disadvantages. It has a major disadvantage. If you look into that, it says the leakage current is very high. So when we design, suppose a power supply, if you are designing, so if it has a very high leakage current, then it will be, you have a very lossy system. Like the wake up, the sleep current itself is very, will be very high. So there are some still there are some work is going on, particularly on the vertical GaN, but it is a future technology, and it can allow a very good advantage for the industry. Like we can operate at very high frequency and very high voltages also. Silicon carbide, it has some advantage, particularly when we go for high current application and like high voltage. But gallium nitride has that same advantages, but there are some restrictions that we will discuss further. Yeah. So if you look into this, like GaN substrate, for GaN on silicon and GaN on silicon carbide, and then third one is your GaN on GaN. So defect density, if you look into this, like GaN on GaN is very low. It is 10 to the power 3. So defect density is like number of defect which is available per unit wafer area. So we are seeing a very low defect when we look into this GaN on GaN. So it allow a very good reliability in the long term. And usually how the semiconductor is manufactured, the cleanliness and the number of total outcomes, overall output of the yield is better if you look into the GaN on GaN. Similarly, the lattice mismatch is very low. Lattice mismatch is like the how the different structure, this lattice structure, particularly GaN or silicon, is merged. So that's there is a mismatch is there, particularly if you look into GaN and silicon, but there is no mismatch in GaN on GaN. Layer thickness also is very high. Second most important thing is reliability, because we want to design a product which is reliable, which is sustained for next 10 years or 25 years. When we discuss about the solar products, it is definitely 25 years. So we have to take into those account, like our semiconductor is good design. It is a reliable product, and when we developing different products for consumer, we should not face any field failures particularly. And device type, if you look, GaN on silicon and carbide is like lateral, and GaN on GaN is a vertical, and as well as lateral, both are available. So, what are the important parameters, like when we select a MOSFET or any switching devices? Particularly, we looked into the RDS on. RDS on is very good for GaN. Switching times, we can switch at very high frequency from 1 megahertz to 3 megahertz. Reverse current characteristics, it is a design dependent, but in some design we need that reverse current. It doesn't have a body diode, but it can do reverse current. But the diode drop is very high for in GaN, the reverse drop. And COS is also very good, particularly for GaN. Gate driver, we will discuss in detail, because gate driver is the important thing, and how you are going to utilize, how to like GaN needs a very design, very need to be in very constant design has to be done, particularly precise design, I mean, for the gate driver and the GaN to be drive. Thermal isolation, this is also like GaN design dependent. High voltage range, there are few GaN devices which are available, particularly GaN system and Xperia, they are providing GaN. Infineon also has recently come up with a different type of GaN, and which is allowing a little higher voltage, like 200 volt, 100 to 150 to 200 volt, but they are still 600 volt are very limited company which are doing it. Cost, when we discuss about cost, it is actually too early to tell, because there are some company like EPC, they are giving at a very optimize as well as like a competitive price to silicon. So we have to look into the design what we are doing. Suppose if you are doing a synchronous puck, then and switching at 1 megahertz frequency, then it is better to go with GAN. But if you are doing a very different inverter circuit, suppose motor controller where you need high current, thermally we don't have that much stability, then we may not go with the GAN, because the performance and the cost is good for silicon. So it is very design dependent, and like depend on our application. Yes. If you look into the history of evolvement, like definitely the power devices has been evolved a lot, like last 8 decade. If you look into this, like 8 to, and there are a lot of application has been in this area, particularly the packaging. Package is very important. GAN package is also very important, because initially, if you select a package which is we are not able to manufacture, then it creates a lot of problems. So look, you have to look into the packaging of the device also. How the device is suitable, like how you are going to dissipate the heat out, how you are going to interface with your heat sink. So those things also need to be looked into. Like there is a top cool fat is coming for silicon nowadays. So gallium nitride has also providing some of the solution. But when you are designing application, we have to look into the package of the tool, because and how you are doing the layout. Yeah, if you compare the in term of the material property comparison, definitely, like I think this is everybody will have idea about this. So definitely the band gap is very high for gallium nitride, is high electron mobility, and thermal conductivity is also good. Then if you look into this Baliga figure of merit is also very high. Baliga figure of merit talks about the on resistance and the breakdown voltage. It's a equation on that. So figure of merits also is very good for the GAN, and electron mobility is also definitely is very high. Yeah. So this is a similar comparison, but this is more into like we are slowly going towards like the details of the technical details of the gallium nitride, and what when we consider for designing, what we need to look into that. So for gallium nitride, RDS on is very low. So which is good, definitely. And for the same current, if you look into this, RDS on is low, and we can switch at very high frequency. So my inductor and all component like transformer as well as the inductor size, we can really reduce it. Second is like the main challenge comes with the VGS range. Actually, for the VGS range is very narrow actually for gallium nitride. It has to be 4.5 volt to 6.5 volt. So whatever the gate driver we are designing, the VCC what we are supplying, it has to be very fixed, because gallium nitride maximum it can sustain is around for the gate to source is 7 volts. So it has to be very tight regulated. I can say like the voltage should be very tight regulated. Whereas for MOSFET, it is a very wider range, 5 volt to 20 volt. And avalanche also not there in GAN, but in the vertical GAN there is is a different way. Like the vertical GAN are designed, it has a avalanche. When we talk about the price, definitely it is higher. But right now, I think for some application, particularly 100 volt, 100 ampere devices, gallium nitride price has been reduced. So we can look into those things. Yeah. So right now, like what are the important parameters when we select gallium nitride? Definitely, we have to look into the input capacitance as well as the output capacitance. Your basically that decides your switching losses. So CIS as well as your COS, we need to look into that. Then what is the my RDS on? The RDS on has to be lower for lower conduction losses. Then no body diode, so there is no reverse losses, and as well as the it reduces the ringing. So but one important thing is there, what we have seen particularly in our application, in our design is the body diode drop is very high when it's start conduction. So it's usually we avoid it, the reverse conduction, by adding a Schottky diode across the drain to source, because we don't want the reverse conduction. And if some application is required to have a reverse conduction, it is always recommended to have a Schottky diode across drain to source. Yes. So next, if you look into the like transformer design, like definitely when we are switching at a very high frequency, we can go for a very compact design, integrated transformer design. When you if you look into this optimizer, solar optimizer, or the onboard charger, we cannot have this type of bulky transformer, which is going for a consumer electronics or for low power, as well as for high power, and which needs daily use. We should have a very small compact design. And right now many applications are going towards, because of this reason, that it has to be a user friendly device, and we don't want to go for a bulky design. So in power electronics, I think like 60 to 70% is magnetics. So that definitely we want to reduce the size of that. So definitely we want to go for a very high switching frequency and try to reduce the size of my transformer or inductor. Yes. Next comes the package. So packaging is very crucial. Definitely, gallium nitride has the advantage of very small package, and it's give us the power density and very reduced size. But also, I will suggest everyone like look into the design from a broader perspective. Like it has to be manufactured. Like it has to be the end of line test. It has to pass all the test. We should be compact design is good, but we should allow the heat to be transferred. So and how this manufacturer is going to solder it, the soldering process, how the layout has been done. So the person has to give importance to those things, because it becomes a very challenge when we were trying to solder it manually, and it cannot be manually soldered. But silicon or any silicon carbide is very we can solder very easily, and the manufacturing process is also very easy. And for gallium nitride, it becomes challenge for is like when we are doing a mass product. So if there is the tolerance of the package is very low, and it has to be very accurately solder, and you need to know that between gate to source, the distance itself is very low, and there is chance that it can short also. So how you are going to avoid that? So we need to have a all the after your assembly, we need to have a x-ray to understand it, and what is the optimum temperature is required. Like we cannot do in a very it has a very controlled temperature to do the soldering, and how to like have a different type of process related failure. So importance has to be given, even though we will have a advantage in term of smaller size, power density, but we will be having trouble while we do a mass manufacturing and process related issues might come up. Second thing is, yes, particularly cascaded GaN high electron mobility is also being used. Particularly if you look into the solar hybrid inverters, they are going with this device. Particularly, it has the advantage definitely, but there are measure. This is basically whatever the advantage you have on GaN on GaN, you will not have that advantage here, GaN on silicon, because here you still have those losses. You have this losses, reverse diode conduction is there, so those losses will come into the picture. But it has in term of reliability, this product is good, because you will have a silicon coming into the picture, and like you will have the control. You give a voltage, you start turning on the FET, your gallium nitride turns on, and if you turn off, like if you go to the negative turn off the your silicon goes to 0 volt, then you will have a negative voltage negative voltage coming up across your gate to source of the gallium nitride, and it will turn off. Basically this is a integration of a silicon FET as well as a depletion mode gallium nitride. So it has some advantage, but there are some, like you can switch at little higher frequency, those advantage you have, but in term of losses, this device will have a more loss. Yeah. So you can look into the different type of company which is like providing a package, because package is very important, as I told you earlier also, like which type of package. We were like very comfortable with GaN system, and GaN system has a 100 volt 100 ampere device is available, and we can easily able to solder it, as well as the manufacturing was also easy. But if you look into this EPC GAN, it is a very challenging device, but it has a advantage in term of like very low COS, and CIS and RDS on is also very low. So in term of the application, it is very good, but in we were a lot of challenges in manufacturing and process. If you compare the chip size over the years, definitely, even though silicon has also done a lot of size has been reduced in the last 20 years, but GAN is like a, you can say, is quantum leap. And even with the lateral structure, it is very we are able to reduce the die size to a very very low. And the vertical GAN technology coming up will have a more lower um, uh, dense die and structure, and we will have able to operate in a very high voltage and high frequency. Yeah. Yeah. So I was discussing about the gate driver. For gallium nitride, there are different parameters which has to be looked into when while we are selecting a gate driver. Basically, the GAN FET have a very low threshold voltage, like zero point 0.7 volt to in the range of 1.5 volt. So we cannot allow a very high ringing. If the ringing is there, then we'll have a shoot through problem, and it can damage your FET. Second is like if you are charging through a boost up diode, then there is a problem that you will be overcharged it. Like particularly gallium FET maximum voltage VGS is 7 volt. So by mistake, if you are charging it to a very high voltage, and if you are like crossing it 7 volt, then there is a chance that it can damage your top FET. Then you have to look into the under voltage lockout. Particularly 3.6 volt is for disable and 4 volt is for enable. So you have to look into those parameters, particularly while selecting a gate driver. And gate driver should have a very high withstand dv by dt. The ringing, whatever, it has to be 100 volt per nanosecond. Then second is it should, if it is an integrated gate driver or a separate gate driver, the minimum dead time we need to keep is 20 to 40 nanosecond. If it is a programmable one, then it is good. Or if you are connecting a register and trying to set a fixed dead time, the minimum is always to keep in 20 to 40 nanosecond. And this low cost Schottky diode, which I was telling, right, in we need to connect in parallel. So this is depends on design, like where the reverse current is very high, and we don't want through the GAN. Loss itself is very high, and we can use this. Then separate turn on and turn off register, like we want to do a fast turn off. And turning on also, we want to control the gate current. And we definitely have to look into the source and sink current capabilities of the gate driver. And so that is why, like, better to have a separate turn on and turn off register. Like turn off you can keep, I think, for if you're switching at above 750 kilohertz, it is better to keep a directly 0 ohm for our turning off register. But our on register you can keep in one ohm to like, let's say, like around 5 ohm. But it depends, like what is the your gate driver capability, your source current capability, and sink current capabilities, and like how you are going to charge your boost up capacitor. And definitely, and one more thing is your gate to source voltage, which is, let's say, from 0 to 5 volt, and how you are going to regulate that. If there is a LDO inside the gate driver, or you are using the source of the gate driver VCC, if it is from the LDO, it is good. Or if there is a more ripple itself on the 5 volt, then we will have a more problem, because if we will not be a very tight control in that case. And we don't have much margin also, because 7 volt is the maximum. And then the over temperature limit protection, if the gate driver allow us to have a temperature protection, it is actually good. But this type of feature, where the gate driver have where OCP, overcurrent protection, as well as the temperature limit protection is there, we have seen usually the cost is little high. So you have to do a trade-off, what is actually required for your application, and what is the target cost, and how still you are able to design for that. Yeah. Second application is like it is the same thing. Only difference in this one is I have used a instead of a bootstrap diode, we can use a same instead of bootstrap diode. I am using again one more gallium nitride. This is basically I want to control the charging current of the my bootstrap capacitor. Same time it is called as a synchronous bootstrap fed circuit, and it's basically performs very well in higher switching frequency, as well as you can avoid some of the, it can eliminate the switching node voltage transition which is we are seeing during the reverse recovery time. Mm, then similarly, like you can try all those things like different turn on and turn off register, one bleeder register, and then we have a two RDM, that damping register, to introduce damping in the circuit inductance. So these are different methods, but I will not recommend all those things to be taken care. But definitely, like the synchronous boost of fat, that is a important things, like which can be actually designed, like you control the charging current of your boost up capacitors, and you doesn't allow overcharging of it. And particularly these solutions are always taken care by the gate driver itself, like the particularly for the gate driver which is designed for to drive gallium nitride in a very high frequency. These features are already taken care, but if there is not available, then like separately some need to be designed. Or if you are using a silicon gate driver or different gate driver, then this design you can incorporate. Yeah. So like next is importance, like how you are doing the your layout design, particularly the controller. Then we have this gate driver and your gallium nitride FET. It has to be designed very optimum. The layer, how you are giving the parasitic, the objective always is to have a very low parasitic inductance, which usually causes a switching loss, then ringing, then reliability issues. And there is issues we have seen, there is a false turn on issues we are observing, and we want to avoid as much possible and in the layout itself. Because if device is good but your layout is bad, then we will lose all our the advantage. We will have a very high ringing, and it will damage either your fat or your gate driver. So, and it is very difficult to do probing also, like when we as a student we will face these challenges, because when we are switching at, let's say, 1 megahertz, and we are trying to see the gate to source voltage, how the PWMs are varying for the top fat as well as the bottom fat. So it will be challenge, because if, unless your probing is 3 picofarad, it is of your, or suppose you are using a very high capacitance probes, then you itself you are introducing one ringing to the system, and it can damage itself while probing also. So these things also need to be taken care, like you have to use a 3 picofarad probes and look into the waveforms. And so the best part is to take care in the PCB layout. You always provide test points while designing. If you are looking, if it is a R&D activity and has been prototype, then better to keep a very clean design, and provide enough test point, and always the ground layer how you are taking care, like it has to be the return out to the gate driver, the your source ground, when it is suppose, let's say, is a buck converter, a synchronous buck converter, and the bottom fat, your source, and your gate driver ground has to be very the layer has to be your, you need to provide enough copper in that path, because you don't want the switching noise again injecting into your gate driver, or it is if these switching noise are injecting, it will be reflected on your controller sound, controller side. You will have issues related to like ground bouncing, where you will have a very high dv by dt, which is reflecting your PWM input, means your gate driver input, as well as on the gate driver output, so which can potentially damage your system. And when you take it for, let us say, EMI EMC testing and all, you will have a very will not be able to pass the narrow band, which has been the criteria. So that is the that is the reason, like many companies like Texas as well as the Infineon, they are providing us this integrated driver solution, where your gate driver and your gallium nitride is integrated to a one solution. So you don't have to worry about the layout and how the loop inductance between your return path. So that is where it has an advantage. Integrating driver eliminates your common source inductance and significantly reduces the inductance between the driver output and the gallium nitride gate, and as well as the inductance in the gate driver grounding. So this basically solves that issue, like the ground bouncing and the common source inductance, which we can avoid. But the disadvantage is like the cost is very high, and with when the cost is high, it defeats the purpose. Actually, we cannot use for this. But over the time, if the cost is reducing, then we can look into this type of integrated driver solutions. So this LMZ 3410 is same, is the integrated gate driver solution, and you can look into this. Like it has a UVLO integrated temperature protection. It's generally cutoffs when temperature you can above your junction temperature or like predefined temperature. And it has a UVLO. So UVLO is very important. You need to disable 3.6 and enable at 4 volt. Then similarly, this LDO dropout regulator, and which has a very tight 5 volt, and which you can give it to your gate drivers to your VGS control. So and similarly, like it has a very low power mode, standby condition, and this solution is good actually. And it is 600 volt, 12 ampere, 70 milliampere. It is a good, but it also has a depends on your design. We cannot use this type of solution in all the, like where we don't have this much voltage. 600 volt design is not there. Then we don't go, like we can go for a different type of gate driver, like 100 volt is also available. But definitely you need to look into the slew rate control, and what is the negative voltage transient you are going to see on the HS pin. So those are the some important things you need to see. And like what is the pin maximum voltages. Yeah. So next, I am talking about a different controller. This is a actually synchronous step-down controller designed LTC 7891, designed by analog device, and this is a very mature device, and we have utilized for our vehicle power supply device, power unit architecture, and it is a very good product. So that's why, like I want to discuss on this also. So you can operate this at a very high frequency, 1 megahertz, and it's a very wide input range, particularly like 4 volt to 100 volt. When we are interfacing, let us say battery 48 volt input to 12 volt, which will be 12 volt will be given to different application, like your dashboard or your CAN circuit or your any music system. So 12 volt is my I want to have the 12 volt, which will be interface to many other power supply application. So LTC 7891 is a gate drive technology fully utilized for gallium FET, and output voltage can be you can design, you can set it to different voltages range, and similarly you can design your inductance. So basically this is a peak current mode control. It's operate in a peak current mode control, and it has a three modes actually. Like you can operate in a brushed mode, or you can operate in a pulse skipping mode, and you can operate in a force conduction mode. So generally, when it has an advantage, I can say during a lighter load. Let's say you have a very light load, let's say around 3 watt or 5 watt power consumption is there. So at that time, I don't want particularly all the synchronous buck we have seen, like with the silicon losses efficiency around like 75% to 80%. But in the light load condition, I want to have a very high efficiency system, let's say around 95%, 92%. So 92 to 95%. So with this one, LTC 97891 and incorporating EPC gallium nitride, you can achieve a very high efficiency during the low power also. You can operate in a pulse skipping mode or in the brushed mode, and you can achieve that efficiency. So this is a very good, it has a very also you can by changing the different register, you can set up your different frequency. It can operate from, let's 100 kilohertz to 1 megahertz. And it has an internal LDO. We will yeah, we will discuss. Huh. It has an internal LDO, or you can externally supply 5 volt to regulate my VGS. But also you can internally, it has a LDO which can give you the from the input voltage V in 48 voltage, it will give you a 5 volt, 5 to 6 volt maximum. So you can use that also to mm, control your gate to source voltage. Second is it has a internal bootstrap synchronous. Instead of a bootstrap diode, it has a bootstrap FAT. So which can be utilized to charge your bootstrap capacitor, and it doesn't allow the overcharging of the bootstrap capacitors. Second is like you can operate in a, it has a fixed dead time, or like different type of you can set, like you want smart zero at that time, or you want to give a very fixed dead time. So in you can set up in this device. Yeah, second is like the feedback. One more important thing in this design is the compensation network. So compensation network is very very important, like how you are giving a it has a internal current loop and external voltage loops. So you need to have the stability has been you should be able to regulate the output voltage, and so in that case you need to design your compensation compensator network very good. You need to do type 2 error transconductance method, particularly for this type of application where you achieve the stability, and you need to do complete you need to find out the pole, and you need to define what is my switching frequency, and what is the in the output side your output capacitor ESR. You need to know how much gain you are getting, and particularly that's why it's very important, like you look into the overall design. Only selecting this device will not help us, because we have to look into the what is the in the output side capacitor, if there is electrolytic capacitor or film capacitor, what is the ESR of that, then what is the inductance, what you are going to select, what is the sense register, and how much gain you are getting. So in based on all those inputs, you can design your type 2 compensator network. Yeah. So this is a complete 48 volt actually architecture. When this is basically tells you the application where different type of DC to DC converter is available, as well as your DC to AC applications is available. And particularly this is a architecture of your vehicle, as well as like different BLDC application like water pump, cooling pump. So basically we are not right now focused on those area, but if you look into the EV architecture, the EV ecosystems. So in the EV ecosystem, there are a lot of opportunity to work on, particularly for the GAN, particularly to DC-DC power consumption. Let's say for dashboards power supply, if you are designing, or if you are designing a charging system, if it is a low power charging system, there is a wireless power charger where we can use interface DC to DC. And there is a home entertainment system. If it is EV for four wheeler, then you have a like infotainment system which need to be powered on. And if there is a vehicle two wheeler vehicle system, then you will have a dashboard system coming into, you have a mobile charging system coming into picture. So all those small power application is basically 15 watt to 20 watts. And we want to design in a very optimized very high efficient system. So definitely we look into this zero voltage switching, or like different type of technology, or maybe it a resonant converter, or you are trying to achieve ZVS for your switches. So GaN particularly help us, and we can incorporate gallium nitride particularly in this design, even though there is like bidirectional charging from grid to vehicle or vehicle to grid. So there is possibility where we can explore more into that area, and we can use gallium nitride in that. Yeah, so yeah, this is the actually the maybe not visible, but definitely you can look into this LTC 7891 data sheet. This is the actually in the internal block diagram. So it has a LDO to regulate the 5 voltage, and then it has a over temperature protection, and then we you have a over current protection also. If there is a short circuit on the output side, you have this over current protection, and it will go into this hiccup mode for like let's say for 15 millisecond for every time, and it will try to recover in that case. So you can look more into this in dataset of LTC, but I'm just giving you the basic idea where how you can utilize this device in your design, and you can use independently how you can control different type of feature, particularly like you want to operate in high frequency, you want to operate in burst mode, pulse skipping mode, or force conduction mode, or you want to design let's say for a small motor controller, and you need to have a switching dead time, very optimized smart zero dead time, where you want to achieve your ZVS also. So this type of this device helps a lot. You we can utilize for different type of, I think we can use it for also this half bridge LLC also. Yeah. This is one more application where the like the totem pole bridgeless boost, and they were able to achieve a very good efficiency, particularly with gallium nitride. And if you look into the silicon device, the size, both dimension size is very high. And similarly, they have. If you look into the gallium nitride, and the amount of the inductor size has also reduced significantly, and we were able to replicate the same whatever the design for has been for megahertz, but we were incorporating in a very low, not that much frequency, but in 750 kilohertz, where we can design and try to achieve the same efficiency, close to around 98% for a like 400-watt system. Yeah. One more important application for gallium nitride is a residential solar power optimizer. Solar power optimizer is basically it is a power converter, and it is a device which sits near to solar panels, and your input, let us say around input will be solar panel input, let us say will be around close to 10 volt to 40 volt, and the optimizer output will be 400 volt, and then you give it to your string inverter for so basically optimizer is it will do panel to panel MPPT, and it will optimize the power from this, and it fits to the grid tie inverter. So the solar power optimizer is very important, and how you are going to is an important application for residential solar power. And we need to design very efficient and reliable product, and it has to be designed for 25 years. So we can go with the gallium nitride in this type of application, where you are incorporating a synchronous buck converter, or if you are suppose incorporating a synchronous buck converter will not give us the isolation which is required, but these are designed also is also in the market. But let us say you are designing LLC converter, then you still we where we will meet the isolation requirement, and from the grid side to the solar PV panel side, and we can still use the gallium nitride, because 100 volt 100 ampere gallium nitride is available in the market, and pretty robust and reliable that is. So solar power optimizer is a very very important and very this is the product which is being used a lot, like either in the US or in the Indian market. Is very good, and gallium nitrate will help us switch at very high frequency, and reduce the overall size, because we cannot put a very bulky optimizer below my roof panel. It has to be very small compact device, and around 500 watt I'm able to optimize it. Even though if there is a setting or anything, I'm able to extract the maximum power, and then feed it to the grid tie inverter. So that is why, like, solar power optimizer are very helpful. And company like Enphase or Solar Edge, or Arca Energy, so they are developing this type of product, solar power optimizer, which is available both in Indian market as well as on the US market. Mm, yeah, and second thing is, we'll be able to use, able to get the safety and the UL standard, because when we talk about the product, it has to be a complete product with the say certification of either IEEE or BIS or UL standard. There is one important I want to talk about is the rapid shutdown, which is UL standard rapid shutdowns. Tell us, like, within 30 meter of the PV panel, inside the PV panel and your solar optimizer, if there is a grid issue or anything has happened, we should be, my PV input voltage should be below 80 volt. Like, my optimizer output, let's say, is 400 output. Like, let's say, I'm my PV input, my optimizer input is, let's say, 40 volt, and my I'm doing a boost, and making it 400 volt, and then I'm interfacing it to the my inverter. So whenever there is any emergency or any fault issue, anything happens, so as per UL standard rapid shutdown, we need to shut down the voltage within 30 second, I think. Yes, 30 second, 20 to 30 second, and we need to bring it below 80 volt. So below 80 volt, if you are bringing it, you need again a rapid shutdown device or kind of a breaker, electronic breaker, in between my DC to DC, or it has to be in between your optimizer or inverter, or it has to be between your grid inverter to the grid. So that's a again a challenges. And usually when central string inverter are connected, it is connected little far from the panel, PV panel area. It is usually outside, or it is in the home wall connected, and the wiring has been done. So that's why that's become a very challenge. Like, definitely you are adding one more device, rapid shutdown device, in between, and you want to shut down it. So when we go for this type of low power gallium nitride device where we can control the voltage actually particularly, and we don't have to add extra device like on the to reduce that voltage. Like, we can immediately shut down. We should have the control to immediately shut down my PWM pulses and reduce the voltage within 30 seconds. Within 30 seconds, I should be able to bring the voltage to below 80 volt. So those are possibility is there when we go for solar optimizer, and when we incorporate gallium nitride design also in that. Yeah. So next, where particularly like onboard charger, where we discussed, is very heavily used, and we have seen like gallium nitride has been used particularly on the PFC side, and we have seen this is like a particularly lot of papers are also available on this one. Like, you can see and explore like totem pole PFC, where gallium nitride, the two switches where we will be using the gallium nitride, and we will have that advantages to reduce the losses, switching losses, as well as the conduction losses, and in the same time the PFC inductor also we can reduce. So this is a very important area where the gallium nitride has been efficient, like being used a lot. Like, all the design, it can be a 6.6 kilowatt or 10 kilowatt. The PFC is designed, totem pole PFC is designed with the gallium nitride to get that advantage, and to get that efficiency, because if you are charging the battery, and if we are losing some, let's say, around 15% in the PFC itself, PFC stage, then we don't want to lose that much power. So that's why, like, for good performance and for efficiency system, we have to go into the gallium nitride technology in this particular area. Yeah. So if you look into particularly EV, as well as the 48 volt mid hybrid, gallium nitride help us in reducing the overall size of the system. It doesn't has to be particular only a limited area, but let us say like if I talk about the BMS battery management system, where we have the on register like controlling continuous on register, a continuous on FET, where you are charging or discharging continuously. You can operate gallium nitride on that one, and we have seen like how the overall size, weight, as well as the BOM cost has been reduced. Even though your gallium nitride as a device is costly, but overall BOM cost is reduced significantly, because we will be not needing that much bulky magnetics. We will be not needing extra protection device, because all the gate drivers which is coming for driving the gallium nitride has come with like the protection of UVLO and temperature protection and all those things, over current protection. So we don't have to do again extra protection, and it saves a lot of bandwidth, and it's simplify the architecture. We don't have to make the architecture complicated. So typical application in EV is DC to DC onboard charger and traction inverter. We will discuss about traction inverter. Yeah. So next is, next is um, traction inverter, like EV. Any EV, it is a light vehicle EV or like a heavy four wheeler. Traction inverter is very important, the important module we can say, and the efficiency, reliability of the traction inverter is very important, and it is a challenges in term of like power electronics challenge, as well as the like the thermal, how you are designing. So the some of the like five parameters I have highlighted, which are very important when we do a traction inverter. The bus bar, like laminated bus bar for of a thin layer of metal separated by insulating material, need to be used, so that we don't have a that much loop inductance, and indirectly it will enhance your stability of the controller, and you don't have to see any heating up issues. So bus bar, laminated bus bar of a thin layer is where we need to go. Then power modules. Power modules, when I talking power modules, means your gate driver, your MOSFET is like, also you can go with the GaN or silicon, but if you are going with the normal silicon, you need to look into like how you are going to take the heat out, like how you are going to interface your heat sink to the power switches. Either nowadays like top cool fat is also coming, where you can on the drain you can connect your heat sink. So that's also you are able to do that. So power modules is also important parameter. Then third is your capacitor, because capacitors are very important. It has to absorb the ripple current, either during your motoring mode or the regeneration mode. So your capacitors, the type of the capacitor, your electrolytic mm, capacitor, if you are selecting, like you need to look into the size and the life of the capacitor. What is the overall life if you are going to get from this, and what is the overall temperature, like because most of the electrolytic temperature capacitor has a limit of 105 degree, and we if you are like hitting it more than 105 degree, chance of failure increases and the life also get reduced. So you don't have to see in a long, we have to see in a very long cycle. Actually, we cannot like say I'm getting a good efficiency and it is running well, but let us say over the 5 year, how my capacitor has reduced, how the life of the capacitor, how it has degraded, or how the capacitor has gone into. So you need to do the complete reliability cycle in this, in term of when we are using a electrolytic capacitors, particularly for the traction inverter. Definitely the safe side is to design keeping the ripple current and the life of the capacitor, and connect how much capacitance is need to be taken care. Fourth important parameters is my microcontroller, because microcontroller poses a very important roles. Like it has to be a very high clock speed. We need to I need to process my current, my speed, torque, and simultaneously at very higher sampling rates. And it has to be a different type of protection zones. If you look into the MCU internal architecture, there should be a trip zones available between my PWMs, and like how I'm going to sampling, what is my sampling rate of the ADC channels, and how fast like I'm able to protect. Like there will be like FOC algorithm running into the motor controller, and we don't want, there are different type of inputs coming maybe from the user in term of your throttling speed or braking, or you are going into resonative mode. So the and plus you are running in FOC algorithm below 100 milliseconds. So my microcontroller has to be able to operate in that much fast, and it has to have the processing capabilities. Usually TI C2000 is very popular, like in the Indian market as well as in the student. C2000 series is very popular, where we have a very high frequency 20 megahertz in the range. And mm, but different type of microcontroller, if you are selecting, we have seen a problem, like particularly the low cost. In terms of cost also, you have to select, because there are multiple microcontrollers are available, but you have to look into the processing capabilities, what is the protection zones, trip zones they are providing. There should not be a overlap of the PWMs, because it will then shoot through and you damage your fat. So definitely you need to look into the clock's processor speed, clock frequency, and then definitely you need to look into the like the overall temperature frequency tolerance of your crystal. If you are using a oscillator, external oscillator, then you definitely need to look into the frequency tolerance. The fifth important is the coolant. Definitely traction inverter, if it is a four wheeler and it needs liquid cooling, and liquid cooling either in term of different mixture is there, water, ethyl, and all those things that you can check. But the cooling technology is very important, like how I'm going to take the heat out from my fat. So double sided cooling or microfine cooling plates, which improve the surface contact. So those things need to be taken care. Yeah. Am I audible? Hello?
Hello, sir. Are you able to hear, sir? No. Hello, sir.
Yeah, can you hear me?
Yes, sir. Yes, sir. You are audible.
Yeah, okay. Can you able to see my screen?
Yes, yes, you carry on.
Okay. So this is one of the important. There is a limitation in regenerative braking, and which I want to like discuss particularly. Yeah. So presently, regenerative braking has a limitation when we suppose my battery is fully charged, and I am giving the user input is my throttle actually, and suppose I am giving a whenever there is a, if you are giving your battery is fully charged and you are giving a negative throttle, so there will be no reason current, because my internal cell resistance of the battery doesn't allow me to charge the battery, because my there is a temperature limitation for like from the BMS point of view, there will be limited in terms of the temperature of the what the cell can see. Like it doesn't allow to go over temperature. And then so in that case, from the BMS side, battery management side, there will be limited that whenever there is a SOC is 100%, and we don't want to um, affect my SOH of the battery. So in that case, we don't have the we don't allow the reason current going into the battery. So there is, it is a kind of a limitation. And but when the SOC is below 80%, we allow the reason current to charge the battery. Second is like uh, this regenerative braking, what we were able to do is like, instead of dissipating the current, we dissipate the dissipating the current to the battery, we dissipate in the motor itself. So maybe this is need more detailed discussion, but overall idea is like in the same case, we are not dissipating to the battery. What we are able to do is like we are dissipating the same current in the motor winding itself. So we are able to utilize because the reason current, if it is a very, it is an uncontrolled current, and it can damage my battery, or it can damage my the capacitors also, like the electrolytic capacitors. So it is a very high current, and it will be very in a 10 microsecond, you will be having, you will be seeing around like 100 ampere, 120 ampere for a 3.3 kilowatt system, let's say. So that current is very uncontrolled, and it can damage either your battery or your inverter circuit. So one idea was to like how to utilize same current, and we dissipate in the motor itself the amount, because in region intense in region, what is happening is like I have the energy, kinetic energy, and I'm trying to give it to the battery to charge my battery. But when my battery is SOC is 100%, then we have the problem, like user will not have the braking advantage, right? So and we want to generate the braking torque, and in the same time we don't want to dissipate in the battery. So we what we are trying to do is we are by the algorithm, we are trying to dissipate in the motor itself. So this is one of the like a patented which we have done, and we were able to file the patent for this. And this is a very good advantage. We don't have to compromise for the rider experience, because when you are leaving your acceleration, so by default you will be going into the regional mode, so you don't have to press your brakes. So your braking pads will not having any long term tear down. So because if you are leaving acceleration, you go to a negative throttle, and you try to whatever the generated power will be going to battery. If battery SOC is below 80%, then you will be charging the battery. But suppose my battery SOC is 100%, and in the same time I want to generate the braking torque. So in that case, we will be dissipating the same power to the motor itself, motor winding. But yeah, like there will be long term disadvantage, like we will be wearing down the motor in the long run. So but it has a like advantages is there, because motor winding will not damage immediately over the period. We need to look into that. Second, one more method is like which I think still we are working on that area. What we'll be doing is, instead of like dissipating the power in the motor, what we will do is we will dissipate the power in the your in the inverter circuit itself. So how is that possible? Like so what we will try to do in that case is like we will be controlling the gate to source voltage of the inverter, like all the phases. And what we can do is we can get to source voltage, we can reduce it. Like if you remember the your gate to source voltage and versus RDS on curve, when my gate to source voltage comes down to around 4 volt or below 4 volt, the RDS on increases very high. So what we are trying to do is like whenever we are intentionally trying to operate in a lossy region of the FET, and where my RDS on of the MOSFET will increase, and in that case the loss will try to operate in the will try to dissipate the power in the inverter circuit itself without breaching the SOA of the FET. Hope I am able to clear this. Like so there is like a two methods. One is like dissipating the excess energy in the motor winding. Second, whenever the battery SOC is 100%. Second is you dissipate the energy in the inverter circuit itself. And so how we are trying to achieve it is by controlling the gate to source voltage of the each FET and trying to operate in a lossy region, or you can say ohmic region of the FET, and increases the RDS on. Controlling the gate to source voltage is a different way or different methods circuit you need, because you need to know the user input, like when the throttle is negative or the person has removed the acceleration. So you need to have that information that and then second is like how to control the circuit. Like gate to source voltage, you need to control dynamically, and it has to like you need to control the gate driver 12 volt or whatever voltage is there. So you need to control in a dynamic way using a circuit, and where you can change the gate to source voltage as you need. You can go to 20 volt where it increases the efficiency, like you operate go to higher voltage, you increase the efficiency. And if you come down to lower voltages, let's say 4 volt, where your RDS on is very high, and you operate in a ohmic region and you have a lossy region and you dissipate the power. So so all these things is being done without compromising the rider experience, as well as you generate the braking torque, which is important, because braking torque, when you want to brake the your vehicle and you want to stop it, and without using the physical brakes. So that is where this technology is very important, like regenerative brakings, and both this we innovation we have patented, and for India and US. Yes. Yeah, if you look into the 48 volt system, particularly like mid hybrid and inverter, there is a clear distinction. Like when you design the system with a GAN system, and when you are designing when you are designing with a silicon MOSFET, like size is completely reduced, like 1/5 of the size and 1/3 of the weight. There is a 12% reduction in power loss, 20% lower in BOM cost also. Like I was telling, like how the BOM is actually reduced. BOM is actually reduced because you don't need bulky inductor or transformer. We don't need excessive passive component. Turn on and turn off resistance itself is very low. You don't need turn off resistor. You can put directly 0 ohm also, and turn on resistor also reduce. You don't need a Schottky diode between to protect the negative voltage transient. So all those things can be avoided. Second is like higher switching frequency. You can design the system to be more stable, and you don't want to see more ripple in the phase current also, which indirectly like make the motor very the motor winding with the losses will be more in motor also. Like its temperatures keeps on rising, and over the period we have seen those losses increase. Like the wear down of motor got damaged, the reliability of motor reduces a lot. So that's why like designing a hybrid inverter with the GAN systems speaks a lot. Like even though design is not easy in term of like how the gate driver and the layout you are making, but overall once the product is ready, it is much safe and much reliable product compared to a silicon one. Also second is like it will help you in the heat sink. Like we don't need a bulky heat sink Also you can integrate, I think nowadays different architectures are also coming where you can indirectly integrate motor with a inverter. Like you can integrate motor, inverter and motor in the same casing. You don't need extra casing. So directly from the BMS we'll have a 48 volt, and which will be interfaced to the integrated motor and motor controller, and which will have the inverter. And you avoid lot of like long wears, the and you avoid lot of losses, and also it makes your vehicle very lighter. Yeah. So traction inverter, this is the advantages. Like you can clearly see like how much loss has been reduced, particularly when you are doing the regeneration, uh, and when you are in city or you are in top speed. So gallium nitrates, you can see a clear advantage is there. And reason is very important, because now we regeneration is the technology, and everybody is trying to do it. Is in two wheelers we have, or four wheeler also we are trying to achieve it. Tesla has also done it in regeneration. So in regeneration, the as I told, the current is very high, and we have a very uncontrolled current, and which is we trying to generate the braking torque, and we don't want to damage my BMS, and we want to dissipate the some amount of power. We intentionally want to dissipate some amount of the power in the inverter. So then we should have that like we then we should be very clear like how we are selecting the device, silicon or silicon carbide or the gallium nitrate. There are also application where you don't have to dissipate on the same device. You can parallelly connect it, silicon carbide or silicon in the circuit, and you operate that switch. When you are going to reason, you operate that switch. You don't have to operate the same inverter switch as you are doing in motoring mode. But in regeneration mode, you can operate the different switch where your RDS on itself is very high for the same amount of the current. So that also help us. So that is, both are different architecture, and both can be taken care of. Like we can design both way. Like you have alternative switch which will help us. So that is why like the mix is very important. Like either we can go with gallium nitrate and we have the alternative silicon or silicon switch, or you have the silicon carbide where we have the more current capabilities and you dissipate the power. Yeah. So yeah, coming to the charging infrastructure, this is one of the like I think I'm almost towards the end, and I'm like to discuss about the charging infrastructure. Like the robust charging infrastructure is one of the major drivers, and people wants to adapt charging network. Like it has to be in every city, and Ather is able to do that. Like it has a India largest two-wheeler fast charging network, and 2,500 plus fast charging, and public charging is available. Also recently, like we have designed this charging connector, which is and BIS has also approved it, which is to be considered as a standard for light electric vehicle in India. And it is kind of one of the fast in charging and fast charging standard in the world, where we combine both AC as well as the DC charging system for small EVs as well as electric scooter, motorcycle, or three wheelers, or the quadricycles, where you have a you want to charge from, you either you can give a DC charging current to charge your vehicle, or you provide your AC charger, AC charging, and you have an onboard charger connected. And with this it has also CAN communication also interface, which will have a control, and proximity control is also there in this case. So this is very important. We can use this. Like these are the features, and lot of vehicles. It is a common standard, and lot of vehicles can use. Like particularly in two EV, two wheelers EV, and as well as the light electric vehicles. Yeah. So Why are these important to market? This is all these innovations and design, and whatever today what I have discussed is basically looking into like how the consumer are going to experience, because finally the product, whatever product or innovation what we are designing, it has to be experienced by the consumer. So that is why it's very important, like we take care of the safety, reliability, and the overall life cycle of the product, and it has to be user friendly. So we have the choice to design a better product with better devices. We should be able to do that. In the same time, we are looking into the economy, of the economics of the sale, like scalability of the product. We are designing for reliability, designing for manufacturing, designing for profitability, designing for like a good product, and marketable product is also very important. So and second is like different type of environmental stress is also there, like different region has a different requirement. When we look into the different extreme weather condition, in some area it is very hot. When we are looking into the solar panels, the solar panel temperature itself is very high, and when temperatures are increasing, the solar cell efficiency is 23 to 25%. And then when you have a very high temperature, your voltage, current, all those things matter, like how you are doing the power conversion. Similarly for EV application also, when we are designing for ambient temperature, it is very good. But when it goes to extreme weather condition, we where the stress on the component, the temperature stress itself is very high, and we face a lot of challenges in that case. And we, whatever design product is not that reliable in that environment condition. So that is why we have to look all those parameters, but particularly like what is the temperature range for each of the devices what we have selected, extreme temperature range. Second is like we usually neglect the negative side of like what is the 0 degree or the negative temperature it can handles. uh, Second is like you we have to look into the overall like overall cycles, life cycle, uh, and like how much thermal stress or the cold stress it can take up. No, and then second is some of the standard also, we need to look for, particularly for IEEE standard 1547, where it talks a lot about the safety, particularly from the grid side. Let us say like you have the rate of change of voltage, or the rate of change of frequency, how you are disconnecting from the grids. So these are like important parameters. And while we are selecting component and designing the overall system, so it is very important. And you have to design for to get the certification. We are not designing only for like industry purpose, like it is mainly for the consumer application, and so it has to be certification. Yes, one more thing I forgot is about the radiation, like radiated and conducted emissions. So gallium nitrate, we have seen like usually the one major disadvantage is with the vertical gain is it has a leakage current, and that leakage current, even though it affects, like when you are designing for the vehicle, there will be different nodes of communication, like your can is communicated like with a different system, like you have a BMS is connected, you have your infotainment is connected, you have a motor controller is connected, and you have a dashboard which is connected. So all those things are basically connected via CAN communication. So since even though it is a very secure communication, it doesn't have that much noise mm, coming up. But and then you have a motor connected, which we have a inside is the encoder, which is giving a digital communication output to my motor controller. So all those communications get affected if there is a radiated mm, emission is there, or even though it is a conducted emission. So all these parameters has to be taken care, like in the subsystem itself, in the designing the subsystems. And we have also seen this leakage current issues also, like how the leakage current keeps flowing through the CAN network, even though there is a CAN supply is isolated. And some let us say we remove the CAN isolation, and we don't need CAN isolation, and we want to operate without isolation in that case to optimize the cost. But what happens is this leakage currents keeps on building, and suppose you remove the battery negative, and you will see a very high voltage coming on the CAN communication line, the common mode voltages, which you will be seeing between your chassis to your CAN line, or different or any of your battery negative between two chassis. So overall it affects completely your system. So common mode voltage has to be taken care. And like when we are designing, we need to design the EMI filter has to be designed precisely. But we should not do over design also. Like sometimes we add more just to for the sake of avoiding solving this issue, we over design sometimes. So that also we need to avoid. And wherever, like in vehicle architecture, isolation is very important. Like battery, either we are sensing the battery, and or suppose your CAN communication is there. So isolation has to be taken care, like when where it is required. We don't need to have the isolation, if it is not really required. Like if you two-wheeler, we don't need that much isolation. Maybe it is like for the gate driver and all, it is one 12-volt with boost up method is enough, and we don't need isolation between battery sensing. And it can be a common ground for a overall complete architecture. But when it is a very high voltage architecture, like 400 volt or 800 volt architecture, electric vehicle system, then we need to have that isolation is required. And we cannot bypass that isolation. And then between your CAN communication, your CAN ground, because CAN will be interface between different modules, so the isolation has to be there between different modules. And definitely the gate driver there selected will be different. It will be reinforced isolation between input to output, and channel to channel isolation also required to meet the safety requirement. ASIL-D safety requirement, if you look, we need to have all those things be there. And second is like EMI, EMC, like each subsystem, it is better to check individually each subsystem, like after designing how much radiation you are getting in the narrow bandwidth, particularly how much if there is any high frequency noise is coming up, or any radiation is there, so that can be taken care in the design stage itself. If but we should have that provision to avoid it, like in the design itself. We should not wait for the end, because in the end we will not be able to change a lot, because once design is ready. And similarly for the communication also, if you look into the vehicle communication, it is definitely the CAN one can also, like 48 volt can you can look into, like because the common mode voltage is very high. Like common, suppose you have a 48 volt system, then you will have you will be seeing the voltage build up to 48 volt. 48 volt means the charging voltage, max battery voltage will go up to 56 or 58 volt. So you will be seeing that voltage build up your battery negative to chassis common mode, and it can damage your CAN communication. So these are very tricky area, like usually not easy to solve. And second is your motor. Motor, we are interfacing through it is a censored motor control, let us say, and we have an encoder interface. Encoder is giving us we are sending a clock, and we are clock in megahertz. Let's say like in 5 megahertz we are sending a clock frequency, and we are getting a encoder data, and encoder data. So encoder data. So this motor communication, to know the position of the rotor, so and with the my motor controller. So it is very tricky, because in we have seen the emission to be high, and it usually better to solve, like we don't keep a very we cannot put shielding everywhere. That is also a restriction is there. So the chassis has to be grounded, the chassis has to be, and how you are taking the grounding of the wire in the vehicle architecture is very important. And what is the clock frequency? If it can be analog based, it is good, because but if it is like digital based, usually now all the encoder or resolvers are digital based, so we cannot avoid that. But in our design itself, mm, we need to take care of all those things, like you provide ferrite bead, you do the shielding of the wire, we try to keep the length of the wire very small and short. So these are some of the optimized methods, and where we can like try ourselves and make it reliable. Yeah. So yeah, then I think almost I am done with my discussion, and we'll like to take some of the question from the audience. Yeah. Yeah. Hello.
Dibyaraj,
Yes. Yes.
yeah, it was a very wonderful session. I think you enlightened how the industry is different than the academic. Okay,
Yeah. Yes.
it's really wonderful, and I think your industry also doing very good. If any queries, dear participants, you can either post in the chat box or in the question answer section. Okay, expert will take care.
So yes.
Dibyaraj, you
Yeah.
can see in the chat box. Okay.
Yeah.
Uh, Also, I am inviting all the participants. They can turn on their mic if they want to ask directly to the expert. They can
Yeah.
ask. Yeah.
Excuse me, sir.
Yeah.
Sir, am I audible, sir?
Yeah. You are audible. You can ask the question. Yes.
Sir, good afternoon, sir, and thank you so much
Yeah.
for wonderful presentation, sir. Sir, I have a very basic question, sir. As you mentioned in the presentation, sir, for high switching frequency as well as for very wide voltage range, we can use gallium nitride, sir. As also you mentioned about the silicon carbide, which is also very prevalent nowadays. So, what are the basic fundamental differences, sir, between these two kind of semiconductors? Please,
Yeah.
sir, explain. Sir.
Yeah. For you can see for gallium nitride, like if you go back to this one, let's go. Yeah, you can see the slide, right? So
Yes, sir.
silicon carbide has a advantage. Definitely, it has a advantage. Like we can operate in a higher voltage, like particularly high current application, where there is a high current and high voltage. We usually go with the silicon carbide, because it is a very industry stabilized product already, means already in the market. But when you look into the GaN on silicon, which is right now in the market, it does it we can switch at very high frequency, but we don't have voltage. Like it has a maximum breakdown voltage of 600 volt, which is available in the market. And if you look into the vehicle architecture, 800 volt is what minimum we need. Or the inverter also, high voltage, high power application. So breakdown voltage is one of the major reason. And the material property also is better in silicon carbide. But if you look into the vertical GaN, which is a new technology, okay, that is still not in the market. Still, it is a future technology, and it is a GaN on GaN, which where you have the breakdown voltage is very high, and also at the same time you can operate at in a very high frequency. So silicon carbide, we don't operate in 1 megahertz or 2 megahertz, but GaN you can operate in 1 megahertz. So that is also one difference is there, like what is at what switching frequency you want to operate. Then second is your breakdown voltage. You can understand like your critical electric field is and how much it is between your during your off stage, what is the voltage you are seeing during the off condition. And it will have a advantage in vertical GaN. Yeah, hope I were able to make it clear to you.
Sir, excuse me, sir. Currently in India, means as you mentioned, Ather, sir. So currently in India, automobiles. So is
Mm.
gallium nitride is being implemented, or SiC is prevalent? So
Gallium nitride is being used, but right now it is used for like low power application, like where you don't see very high voltage. Let us say, as I told, na, wireless power application, where your maximum voltage is 100 volt. Like let us say you in our vehicle architecture, it is only 48 volt architecture. So maximum voltage you can see, let us say, is around 80 volt. Let us in the worst case. So we can use GaN in that case, where your 100 volt 100 ampere application is there, so you can use. And in India as well as outside also, GaN is being used, particularly low power application. But in high power application, we still are going with silicon carbide. Yeah.
okay, sir. Thank you, sir.
Yeah. Yes. Yes. Yes, you can ask the question.
Hmm. Yes, my
Yeah.
question is
Yeah.
regarding one question was like that, but GAN is high temperature, high voltage application that normal GAN is not providing that for high voltage that you were talking about
Ha
silicon
ha.
carbide.
Yeah, yes, yes, yes. For high voltage, temperature is one thing, because the temperature both are stable only. We don't see challenges in term of temperature. But when you look into the voltages, breakdown voltage, that is very high. Like if you look in the GaN on silicon, we have a limitation of breakdown voltage of maximum 600 volt. And
Uh,
silicon carbide, you can go into higher voltages. But when we this new technology vertical GaN, there we have the advantage completely. The green section you can see, like I have the advantages of both. I can operate at higher frequency, and I have the higher voltages also.
Okay, then the electric vehicle, that automatic electric vehicle that are coming up without
Yeah.
without any driver or whatever,
Huh.
that
Mhm.
automatic vehicle will be controlled by this vertical GaN. It is expected that by vertical GaN, or it will be off loop, because the voltage is 48 volt we require na, for
Mhm.
battery
Mhm.
charging and others. But I think
Yeah.
for other purpose also, for your
Yeah. Yeah.
the condition purpose, the frequency should be very high for switching
Yeah.
frequency.
Yeah. Yes, yes. See, vertical GaN is very new technology, and I think, if I am not wrong, we are like 10 years to reach to fully mature that technology on vertical GaN. Okay, so right now we can discuss only on GaN on silicon device. So where you have the, like as you told, like particularly in EV, for two-wheeler EV it is 48 volt. For a four-wheeler it is 400 or 800 voltage. Yeah, yes, yes. So when it is a high voltage right now, let us say 800 volt, you can go ahead with silicon carbide. And if it is below 600 volt, and you can go with silicon gallium nitride in this case.
Okay. And the thing
Yeah,
is,
yeah.
everything is, we are talking about switching, but
Yes, yes.
what is the condition of if the switching is with solar, if it is coming from solar and other sources? So within
Mhm.
this environmental issues, really we are
Mhm.
providing or like utilizing the
Mhm.
same frequency for taking the maximum power, and you are talking about one optimizer. So that, what
Mhm.
is the difference between PCU, power conditioning unit, MPPT, and
Mhm.
what is the
Mhm.
advantage of that
Optimizer.
optimizer?
Yeah, see, optimizer, solar power optimizer is actually is a it is a normal converter. Like it can be a your buck converter, or it can be a resonant converter. So, but it is incorporated with MPPT. Let me show you the block diagram. Uh, See, yeah. So in this one, you can see like the input is my PV, and output will be, let us say your PV will be in the input voltage of range, let's say 10 volt to 30 volt, because throughout the day my panel temperature, based on temperature, my voltage will keep on vary, right? So it will vary from 10 to 40 volt. But I want to have a output voltage in a different, like let us say it is a buck, or it can be a boost. Okay, so I want 100 volt, or let's say 400 volt. So and the same time I want to have a MPPT running. MPPT is maximum power tracking. Like I want to extract the maximum power from the PV itself, and then we want to feed it to the grid. So it is basically a optimizer, because we are optimizing to the ambient temperature, and based on the temperature we want to optimize it, and we will be controlling in that way.
That is in the power conditioning unit, is it
Yeah,
within
yeah,
the
yes.
power? Uh,
Yeah, it is. You can same. It is just a industry name. Optimizer is just a like a name only, namesake. But the purpose is power condition unit is also same. Like, but depend on like what is the power rating. Like, basically the solar power optimizer are like maximum like 400 watts to 500 watts. It doesn't go more than that. And you should have that. I talk about the rapid shutdown, right? You should have that safety standard, because we don't want to put a very bulky or power conditioning unit below my panel. So that is why like these are called solar optimizer.
okay, okay.
Yeah, yeah.
One thing, and very low voltage. What do you feel that, because
Yes.
for maintenance and other purposes, if we are for consumer use, if one can
Mhm.
think of low like less number of photovoltaic panels or others, so that
Uh-huh.
everything, the BOS will be less and everything will be of low cost. So that will
Yeah,
be
yeah.
better for consumer, or because even if it is a single or two
Mm-hmm. Mm-hmm.
kind of
Optimizer. Huh.
optimizer, low voltage optimizer, then it would be of great importance, or it would be like that we are getting 70% of the total what we are estimating from the installation point of
Yes.
view. After that, we are getting almost 60 to 70% of the total energy. So in that
Yeah.
case,
Yes.
really our inverter is not, or the conditioner or charge controller are not taking care of the microclimatic conditions even. So can
Mhm.
it be incorporated in that way also?
Hmm. Yes, yes. Actually, you asked the right question. See, when you looked into this conventional architecture, usually you have a power conditioning unit, and then you have the inverter placing into that. But it doesn't take care the panel wise. Like individually, panel wise, we don't optimize it. Like let us say in a 25 kilowatt, you let's say 10 kilowatt, you have, let's say, five panel. Okay, if each of 2 kilowatt, but we don't do optimization for each panel. But
That is the
utilizing the
problem.
solar. Yeah, yes. So you
in
can
that
use
case,
this power optimizer. Yeah. Yes.
that the
Yes.
low power
Mm.
optimizer can be possible also, like
Yes.
1
Yes. Yes.
kilowatt or that
Yes.
kind
Yes.
of thing.
Yeah. Yeah.
Okay.
Yes.
So
Yes.
which
Okay.
company in India it is available?
So right now, I think there is a company called Solar Edge. It is a US company, but they have the product Solar Optimizer. You can look into that. And second, one more company is there you can look into is Enphase. So Enphase, what they are doing is they are directly making it from the low power, transmitting it to AC. What basically they are doing is for a low voltage they are directly
Yes.
giving it to grid, means you don't need again a like a inverter, string inverter for the interfacing. So it will be AC parallel. Okay, on DC optimizer is it will make DC parallel and then goes to inverter, but in if it is a micro inverter, it will be AC parallel.
Okay. Okay. Okay.
Yeah, yeah,
Thank you, sir. Thank you.
yeah.
So if we really have question, we can connect you for our
Yes, yes,
any
yes,
issues.
yes, yes, yes,
Okay.
yes,
Thank
sure.
you.
Yeah,
Thank you so much.
yes, yeah, thank you.
If any other queries, participants.
இன்னும் முடியல. சரி, அதான் நீங்க இப்போ இடையில வந்த மாதிரியே தெரியலையே, அதுக்கு தான் நானும் க்ளோஸ் பண்ணாம உட்காந்துருக்கேன். நீங்க போட்டீங்களா இல்லையா? சரி சரி, அதான் நீங்க போட்டீங்களா போடலையா?
Madam, please mute your mic. Yeah.
ஆமா, இவர் நல்லா பேசுறாரு. இந்த செஷன் நல்லா இருக்கு ஆக்சுவலா.
Okay. If you don't have any queries, I request all of you to please turn on your camera so that we can take a snapshot. Also, after this, you can check, I think in the chat box, we have shared a feedback form, come attendance sheet. Please fill it up. Please open, I think we have given the permission to turn on your camera. Participants, please turn on your camera so that we can take a snapshot. We have taken. Thank you. Thank you all. Thank you, Dibyaraj.
Yeah, thank you. Thank you, everyone.
Excuse me, sir.
Yeah.
Yeah,
Yeah, I
yeah,
think
you
one.
can ask.
Sir, can
Yes,
you
yes, you
please
can ask.
share the attendance form in the question answer section? Because I'm unable to open the chat box now.
Okay, okay.
Thank you, sir.
Yeah. So I think Monorojan sir will share the contact. If anyone has any question or like wants to know about this, we can discuss also. Like
Yeah, yeah, sure.
you can
We'll
ask share queries.
we'll share the PPT by the expert, whatever we
Yes,
shared with. Okay, to us. Also, we have the recordings. Okay, so
yes,
that will
yes,
be, I think, greatly help for the participant. Yeah.
yes, yeah, yes. Thank you, everyone. Yes,
So our hello.
yes,
So our schedule will be starting tomorrow, the day 2 of this workshop. So we will be expecting your presence sharp at 9 o'clock tomorrow. That is 9th of June 2024. So any further changes or any sort of communication, it will be communicated through the WhatsApp group as well as the Microsoft Teams that we have already prepared. So today we could be able to get number of concerns from the participants that they are unable to get any sort of chat options also. The main reason behind this is that your accounts are not being verified. So kindly go through the process and verify so that you can be able to access all your all the features which is enabled onto Microsoft Teams. So thank you very much for joining with us, and with your kind support, the day one has got a successful one. Thank you very much. So we are signing off for the day.
Thank you, sir.
Sir.
Hello, admin. Thank you, sir. Thank you. Hello.